In fact, I switched over my computer's audio source so that I'm talking to you right now over the preamp we just designed. Hi, I'm Kevin. Welcome to my cave. Last time in our series on op-amps, I promised to present the AC Amplifier, a configuration that can amplify an AC input signal with extremely high gain, perhaps in the thousands, while discarding any DC offset. For my example circuit, I'm going to use one of these little Electret microphone capsules. They're pretty ubiquitous. This is just one that I happen to have in my junk box. I'm going to pretend that I want to connect the mic to an A to D converter attached to a microcontroller. As a further challenge, I want the entire system to run off a single 5-volt supply, no plus or minus 12-volt rails. A lot of these A to Ds have an input range of 0 to about 2 or 2.5 volts, so I'll want the output to have a DC bias of a little over a volt. We'll soon see that there are a few challenges putting all of this together. The Electret microphone is itself an interesting device. It depends on the property of some materials to have a permanent electrical polarization. Those materials are called electrets, a portmanteau of electrostatic and magnet. An electret material separates charge, being positive on one surface and negative on another. You can think of it as being a permanently charged capacitor. The phenomenon was known as long ago as 1762, when the Swedish physicist Johan Wilcke built a device using pitch as the electret, and showed that it could repeatedly charge a metal plate brought in contact with it. A few years later, Alessandro Volta improved the device, which he named the Electrophorus perpetuus, Latin for perpetual bearer of electricity, and brought it to a wide audience. Of course, Volta went on to invent what we now know as the electrical battery, and his Electrophorus was relegated mostly to being a laboratory curiosity. The Electret remained mostly a curiosity until James West of Bell Labs, while studying condenser microphones, discovered by accident in 1957 that a piece of metallized mylar film could be permanently charged as an electret. By 1962, he had produced the first foil electret microphone, a design that's used in nearly 90% of the microphones produced today. So how does a permanently charged plastic film let us build a microphone? Well, we stretch it as a diaphragm across an aperture. We ground one side of it, and the other side will have a charge relative to ground. Of course, sound waves will make the diaphragm vibrate. Now we put a conductive plate behind the electret. Electrostatic attraction will separate charges in the plate, and it will look like a charged capacitor. Pulling current from the capacitor will drain the charge, but the charge will restore itself once there's no load. You might think such a thing would be a perpetual motion machine, because you can keep drawing little bits of current, but you'd be wrong. I won't get into the details here, but it can be shown that the act of making and breaking the connection to the load takes more work than you can derive from the system. For instance, in the Electrophorus, when you separate the plates, you have to do mechanical work to overcome the electrostatic attraction between them. The Wimshurst Machine, a 19th century static electricity generator, works on a similar principle of charge separation, with the mechanical energy supplied by a crank. The capacitor we've created will have some plate area A and some separation D between the plates. The dielectric material between the charged plates is air, so we can treat it as having a relative permittivity of 1. We know the formula for capacitance given the capacitor's geometry. We also know the formula for how a capacitor behaves in circuit. We can rearrange terms, and we discover that the voltage we expect to see across the capacitor is directly proportional to the distance between the plates. That confirms this device is a microphone. If we subject it to an oscillating air pressure, and that's what sound is, then we'll get a proportionally oscillating voltage. Before we continue, let me interrupt for just a moment. Longtime viewers of this channel will know that it's always free to all comers. Nothing is ever paywalled. But I do end each video asking one thing, that you take care of one another. To that end, all the advertising revenue that I earn from this channel goes to charity. The current featured charity is called Hare International. Hare's mission is to end hunger and poverty in partnership with the communities it serves. It begins with a seed investment in livestock or agriculture, together with mentorship to help its participants build a business. The participants, small farmers, ranchers, and female business owners, are able to learn a living income and continuously lift up their communities as they train the next generation of leaders. I'd like to ask you to join me in supporting this organization. I set a goal of $500, which is enough to give a cow to a family in need, together with training and education in how to care for her and how to access the market for her milk. I know that with the generosity of Kevin's Cave people, we'll just crush that goal. Won't you help out today? There's a link to donate, up here, or down there, or at any rate somewhere nearby. Thanks so much, and now back to the video. Let's use the usual schematic symbol for a microphone to denote this element, with a tiny capacitor symbol inside to emphasize what type of mic it is. Because the relation between pressure and voltage is valued only when the output current is negligible, virtually all the microphone elements on the market incorporate a JFET amplifier built into the capsule. The circuit designer is expected to include a pull-up resistor outside the capsule, and the datasheet will ordinarily specify what voltage and resistance to use. The JFET is a common source amplifier, and its output impedance will be just the value of the pull-up resistor. Its output voltage is still going to be quite tiny, often a few millivolts peak to peak, and the manufacturers are not great about specifying what offset that voltage is going to be centered around. It tends to vary quite a bit. The problem of the variable offset voltage is one that we've encountered a few times before, and we know how to fix it for AC signals. Just drop in a high-pass filter. I intend eventually to send the microphone signal into an A to D converter, which will be in a microcontroller system. There will likely be a single 5 or 3.3 volt supply, and the A to D may have a range as low as 2.5 or even 2.2 volts. So I'll set the center voltage to about 1.1 volts. As an exercise, look at the resistor values I used and verify that I got it right. Also, check that I have the input impedance high enough, assuming no load on the RC network. Find the corner frequency, and verify that the filter won't appreciably degrade the audio. I'll hand you the answers over on the project GitHub. Within the frequency range of interest, we now still have an output impedance of 2.2K. That's awkwardly high, so we'll want to add an op-amp buffer. What's more, that FET circuit is still going to be putting out a tiny signal. Maybe a millivolt, maybe a few tens of millivolts. We're going to need gain. So let's put a divider in the feedback loop. The Electret and FET characteristics, and for that matter the loudness of the source, are going to vary all over the map, so the gain will have to be variable. We need a potentiometer to control it. A range of about 10 to 1,000 for the gain is usually pretty good. But wait a minute, what reference voltage can we use here? You can probably see the problem here. The output is going to be unbelievably sensitive to this voltage. With a gain of up to 1,000, an error of a few millivolts here will be an error of up to a few volts on the output, and we have only a 5-volt range from one supply rail to the other. I don't think a simple non-inverting circuit with gain will work here. Fortunately, there's a relatively easy fix to our problem. We change the feedback circuit to a low-pass filter by putting in a small electrolytic capacitor to ground. This is another example of the principle that a monster in the feedback loop is an anti-monster in the circuit response. The op-amp circuit overall will be a high-pass filter. Let's get a quick overview. At DC, the capacitor will look like an open circuit, and there will be no current in the lower branch. The op-amp will simply operate as a unity gain buffer. That's exactly what we want. The bias resistors have already set the voltage, and we want that voltage to feed through to the output. On the other hand, at signal frequencies, the capacitor will look like a short circuit. The circuit will function as an amplifier with a gain of 10 to 1,000 depending on the setting of the pot. Again, that's exactly what we want. We're almost there. But there are a few practical matters I want to run through. We've got a few specific requirements for the op amp. I already said that I wanted to run off a 5-volt computer supply, so it needs to have a power supply span that goes down that far. Lots of newer op amps will fit that, but the NE5532 that I was thinking of using is spec'd for 10 to 30 volts. On top of that, the op amp needs to be ground sensing, meaning that its inputs can go close to the negative supply rail. That rules out cheap JFET types like the LF411 or TL071. The TL071 infamously needs its common mode signal to be at least 4 volts up. Finally, we want the input noise to be as low as possible. We have a fairly low impedance source, so I'm not terribly worried about current noise, but I am about voltage noise. I've seen at least one cheap preamp that uses an LM358, the quintessential cheap BJT input op amp. It works, but it's not terribly quiet. What I finally settled on was the LMP7731. Its rail-to-rail input-output is really quiet, with a voltage noise of about 3 nanovolts per root hertz, and it's designed to operate at low voltage. Unfortunately, I don't have any on hand, and I really need to get moving on getting this video out. So for the prototype, I'm just going to go with the CMOS LMC64H2. It ticks all the boxes except for voltage noise, and it's at least no worse than the cheap LM358 I've seen used elsewhere. Now onto the potentiometer. It too has a challenge. Because we're working with an audio volume, we will want a log taper pot. But that will have the problem that increasing the resistance to its maximum value, turning the knob all the way clockwise, reduces the gain of the amp to its minimum value. So what we want here is reverse log taper pot. The manufacturers' catalogs have a reasonable selection of these, but the distributors tend not to stock them, or at least not to stock them in the compact sizes I use, and I don't feel like ordering a few thousand of them. So for right now, I'm going to put up with a gain control that works backwards. If you can't find a suitable reverse log taper pot, but you have access to a 3D printer, another approach is to make a knob with numbers that run clockwise and put a pointer on the front panel of your device. It'll still feel wrong, but at least the visual feedback will be right. I have a schematic of this whole circuit up on the project GitHub. There's a link in the video description. In addition, I've added an output amp using the conventional plus and minus 12 volt supplies to translate the output to something compatible with the computer's line input, so you can hear how the amp performs. Here it is on the breadboard. I've used a conventional log taper pot for the gain control, so unfortunately it does work backward. If I probe the mic output directly, all that I can see with DC coupling is that it's floating with a DC offset of about 4 volts. If I switch over to AC coupling and change to a 1x probe, I can see the output signal from the mic at the level of a few millivolts. There's a ton of noise, but I think my circuit is innocent. The noise doesn't go away when I turn off the power to it. When I look at the preamp output, things are much happier. The signal oscillates around a bias level of about a volt, pretty much what I wanted. And the noise is low enough that the scope has no trouble locking onto a periodic input signal, such as you can get from a musical instrument. In fact, I switched over my computer's audio source so that I'm talking to you right now over the preamp we just designed.
It's not great, but it would certainly serve for telephone quality audio into a microcontroller. A high-quality low-noise op-amp, a battery-powered front end to isolate the system from the power line, and proper low-noise PC board layout would make for an entirely serviceable preamp.
I hope you enjoyed this detailed look at how a high-gain preamp can be designed. If you did, perhaps you should consider whether I've earned your subscription today. There's a lot more coming in the op-amp series, but first I want to get back and cover a few more issues in the transistor series, particularly exponential and log circuits. I hope you'll stay tuned for all that. Stay safe, stay healthy, stay curious, and take care of one another. Bye.